All right, in this screencast, we're going to go through the entire Unit 2 study guide. First question. Are the following two electrons on the diagram below absorbing energy or releasing energy? How do you know? Which electron had a greater change in energy? How do you know? Well, if you look at the diagram here, you are going from A out here down to this level right here. And then from here, we're doing the same thing. We're falling to a lower energy level. So in both cases, you are releasing energy. Okay, how do you know? Well, obviously we're falling from a higher energy level down to a lower energy level. And electron A is going from energy level 4 to energy level 2, which is a much higher energy level change. So it went from 4 to n equals 2, which is a much higher change than the other one, which went from 3 to 2. All right. Question 2. Fireworks contain different elements whose atoms are energized when the firework is ignited. What happens when an electron in the ground state absorbs energy? So when we heat it in the flame test, we're moving those electrons up to the excited state. So jumps to excited state. And that would mean we're going from here to a higher level. What happens when the electron falls back to the ground state? What do we call this energy? So when the opposite happens, when we fall from a higher state down to a lower state, energy is released in the form of a photon. Okay, and that's what the energy is called. So the photon is kicked out here, like that, and that is what our eyes pick up during the flame test. Why does every element produce a different color light? Well, no two elements have the same difference in energy. No two elements have the same difference in energy. E-N-E-R-G-Y. All right. Following orbital filling diagrams are for carbon. Circle the error and explain why it's incorrect. So the first one, we've got an error right here. Okay, we need to have opposite spins on our electrons when they're paired up. All right, the next one here, we have a mistake in the 2p. So we always want to fill, so here's the 2p, we always want to fill each one with an up arrow before we go back and double those up. Okay, so we went ahead and doubled up before we did that. In C, our mistake is here. You can't skip. Okay, draw an orbital filling diagram for nitrogen. Okay, so nitrogen, if we look at our periodic table, nitrogen is number 7. So it has 7 electrons. Okay, we're going to fill these in order. 1, 2, 3, 4, 5, 6, 7. Done. Okay, sodium is next. Sodium is Na. It's number 11 on the periodic table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, write the electron configuration for the following neutral atoms in the notation of your choosing. Okay, so let's start with oxygen. We'll do it the hard way first. So oxygen is number 8. It's going to have 8 electrons. So I'm going to do this shorthand first. So for oxygen, when we write out shorthand notation, we go up and we start at hydrogen. Okay. So when we do this, let me just do it like this. Let's just do a quick recap on all of the blocks and levels. So bear with me for just a second. Let me go ahead and add this in. All right, I'm going to just plop this in on this empty page here. Okay, so on the periodic table that we use in class, we have 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Those are the S and P blocks. 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B. That is the D block. Okay, so let's just go ahead and label this. This is our S block. In the middle here, this is our D block. And then on the far right here is our, whoop, I made a mistake. Let's fix that. Helium is actually part of the S block. It looks like it's part of the P block, but it is part of the S block. So let me go back and, so this actually fits in right there. Okay. Down below we have the F block right here. This fits in on our periodic table right here, but we are not going to see anything on the F block for our class. Now, if you look on the left side of the periodic table, these numbers correspond with the period that you're in on the periodic table. Okay, so we always start right here. Always start here, unless we're in noble gas notation. So we always start with the 1s block, first space S block. And we are going to oxygen. So we go 1s, 2s, then we go down to the next row. This is going to be 2s1, 2s2. We go across to the other side of the periodic table. This is 2p1, 2p2, 2p3, 2p4. Let's go back and let's fill that in. Okay, so we've got 1s2. That's not what I wanted to do. We have 1s2, 2s2, and then it was 2p4. Remember, easy way to check this is to add up the exponents. The exponents should add up to 8. We add those together, which is the number of electrons that we have here. Okay. Chlorine. Let's take a look at where chlorine is on the periodic table. Chlorine is number 17. So we're going to keep counting here. So 2s, we would fill all the way up, or sorry, 2p6. That'll end at neon. We're going to go down to the third row, 3s1, 3s2. We go across to the other side of the periodic table, 3p1, 3p2, 3p3, 3p4, 3p5. So we had 1s2, 2s2, 2p6, and then 3s2, and then 3p5. All right, gallium. Gallium on the periodic table. Gallium, Ga, is, where's gallium? Gallium's right here. So we're going to do noble gas notation for gallium here, just to change it up a little bit. So for noble gas notation, we're going to go backwards until we get to a noble gas. The noble gases are this last group, group 8A, on the periodic table. So if I count backwards, 30, 29, 28, and so forth, 19, 18, argon is in the noble gas group. Okay, so we're going to start by writing out argon. And then we're going to continue our electron configuration from there. So from argon, we go down to 4s, 4s1, 4s2. This is the D block. Remember, the D block is 1 period behind. So instead of it being 4D, it's going to be 3D. 3D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it's going to be 4P1. So we said 4S2, 3D10, and then 4P1. So the noble gas notation is a shortcut. Instead of starting at hydrogen, we're going to start at that noble gas. Okay, number 6 says identify the following atoms based on their electron configuration. Okay, I'm going to show you a shortcut with this. If you just look at the last piece, so it says 4p3. If I go to my periodic table, I go down to the 4th row, P block, 1, 2, 3, that is going to be arsenic. Same thing, let's go to B, it says 4D9. So if I go, remember the D is one behind, so instead of going to the 4th row, we're going to go to the 5th row, and it was D9. So here's D1, 2, 3, 4, 5, 6, 7, 8, 9. Should be silver. And the last one here, 3p3. 3rd row, P block, 1, 2, 3. It's going to be phosphorus. All right. 7. The electron configuration of a fluorine ion is 2, 4, 10. So there's 10 electrons that are here. Fluorine normally, if you look here, fluorine normally has 9 electrons. So an atom of fluorine has 9 electrons. So it went from 9 to 10. So instead of having a neutral atom where you have 9 electrons and 9 protons, we now have 10 electrons and 9 protons. So since we have one more electron, our charge is going to be -1. Same thing with sulfur. So we've got 2, 4, 10, 12, 18. And if you go and look, sulfur is 16. So we went from 16 to 18. So in order to, if we gain 2 more electrons, our charge will be -2. All right, potassium, 2, 4, 10, 12, 18. Okay, and then potassium is normally 19. We went from 19 to 18, so we lost an electron, so our charge will be +1. All right. Predict the charge of the following elements when they ionize. Okay, so we're going to go down back to our periodic table that I had here. And I'm going to erase some of this so we can write again. Okay, so charges have to do with valence electrons. So let's just go through this. So we are not going to do anything with the middle here. Okay. So everywhere it says where there's a B, so like 3B, 4B, we're going to ignore that middle section for right now. We're only concerned with 1A, 2A, 3A, and so forth. That number in front of the A tells you how many valence electrons you have. The valence electrons, remember, are the electrons in the outer shell. This is where the valence electrons exist. They're in the outermost energy level. Okay? All right. Now, if you have between 1 and 3 valence electrons, you're going to lose those. So again, here's our Bohr model. So if I have 1 valence electron, that means I'm going to have a bunch of other electrons below that if I'm on the 3rd energy level. So rather than finding 7 more electrons to fill up my outer energy level, if I just get rid of that one, now I have a full energy level below it. Okay, so it's easier to get rid of those electrons if you have between 1 and 3. If I lose an electron here, my charge will be plus 1. If I lose 2 electrons here, my charge will be plus 2. 3 will be plus 3. 4, 4 we can go either way. Okay, so we can either gain or lose. We're going to ignore that for right now. Okay, group 7A only needs 1 electron to get to 8. So if we gain an electron, it'll be minus 1. 6A needs 2 electrons, and then 5A needs 3. Group 8A, remember, is the noble gases. They're already happy, so we're not going to gain or lose any electrons there. All right, so let's go back up and take a look at this question. It says predict the charge. So aluminum. Aluminum is in group 3A, so its charge will be plus 3. Phosphorus is in group 5A. Remember, it's easier to gain if you're closer to 8. Phosphorus is going to gain 3 electrons. Its charge will be minus 3. Oxygen is in group 6A. It's going to gain 2 electrons. Calcium, Ca, is in group 2. It's going to lose those electrons, so its charge will be plus 2. Sodium, Na, is in group 1. It's going to lose that 1 electron. And then bromine, Br, is in group 7, right here, 7A. It's going to gain that electron to get to 8. All right, calcium. When calcium ionizes, it's going to gain or lose electrons. So let's take a look at this. Calcium is in group 2. It is going to lose electrons, and it's going to lose 2. Chlorine. Chlorine is in group 7. It's going to gain an electron to get to 8. Aluminum is in group 3A. It's going to lose 3. Oxygen is in group 6. It needs 2 to get to 8, so it's going to gain 2. Okay, it says which group of metals are the most reactive? Well, group 1A are the most reactive. They only have 1 valence electron. They only have 1 electron in that outer shell. It doesn't take a lot of energy to get rid of that. Okay, so again, you've got your atom here. It only has 1 valence electron. It's really easy to lose that valence electron, which means that it's going to be more reactive. Which group of nonmetals are the most reactive? So remember, we have our staircase on the periodic table. Everything to the right of that staircase is a nonmetal. Everything to the left of that staircase is a metal. Everything on that staircase is a metalloid. So group 7A, right here, these are the most reactive. They have 7 valence electrons, and it only takes 1 more electron for it to be stable. So it's going to do whatever it can to get that 1 electron. Group 7A. Okay, so again, it has 7 valence electrons. It really needs to get that last electron. It's going to do whatever it can to get that last electron. So they are very reactive. All right, which group of elements on the periodic table are the least reactive? That's going to be our noble gases. They have a full outer shell. They are totally happy, and they could care less about gaining electrons. Okay, so our noble gases have a full outer shell. They have all 8. They are not going to want to react. They are totally happy. All right. Which of the following elements is most reactive? Aluminum, sodium, or magnesium? So we've got, let's see, aluminum, magnesium, and sodium. Okay. Now, just a quick recap. Let's go back to our periodic table here. Okay, and let me clear this up. As we move down a group, okay, so remember the groups are the vertical columns on the periodic table. As we move down a group, we are adding an energy level. Okay, so as we go down, we're making our atom bigger, like this. Okay, that's as you go down. As we go down, our valence electrons get further and further away from the nucleus. As they get further away from the nucleus, it's easier for those electrons to get plucked off and be more reactive. So our reactivity increases as we go down a group. As we go from left to right on the periodic table, the number of protons that we have increases. Okay, more protons equals more pull. What happens is it shrinks your atom. Okay, it brings those valence electrons in closer because there's more of an attraction. Okay, so as you go from left to right, it's going to pull those valence electrons in tighter, and it's going to be less reactive. So the most reactive element on our periodic table is this lower left-hand corner where you see francium on here. That's the most reactive. So let's go back and let's look at the three that we had. They were these three. We had sodium, we had magnesium, and we had aluminum. They're all in the same period on the periodic table. So we want to look at where they are from left to right. Sodium is the most reactive because it has the fewest number of valence electrons. Sorry, it has the fewest number of protons. So it will go sodium, then magnesium, and then aluminum. Oops, I have that backwards. Most reactive. I went from highest to lowest. So let's fix that. So we went aluminum, then magnesium, then sodium. Sodium being the most reactive. Okay, the next one we have is sodium, potassium, and lithium. So lithium, sodium, potassium. As we go down that group, remember the atom gets bigger, our valence electrons get further away from the nucleus. So potassium is going to be the most reactive, then sodium, and then lithium. Lithium is the smallest. The valence electrons are the closest. Okay, so most reactive is going to be potassium, then sodium, and then lithium. So potassium will be our most reactive. All right, moving right along. Which of the following elements would be most reactive based on their electron configuration? Okay, 3s1. So our valence electrons are in the S and P block. So here you have one valence electron. Here we have two valence electrons. Here we have one valence electron. Here we have, we're going to ignore the D block because the D block is always one behind. Here we have 4 valence electrons. Okay. So between the 3 that we have left, the fewest number of valence electrons is going to be the most reactive, so we can eliminate this one here. So between argon and neon, let's take a look here. So let's see, argon and neon. So we're looking at either something like potassium or sodium. So the one that's further down is going to be more reactive. So if you look here, this one is in the 3rd period. This one's in the 4th period. So this one has 4 energy levels. This one here only has 3. So the valence electrons are a lot further away. It's going to be more reactive. Okay, which of the following would have properties most similar to fluorine? Most similar to fluorine. Okay, let's see where fluorine is on the periodic table. Fluorine has 7 valence electrons. In order for something to be similar, it's going to have the same number of valence electrons. So here we have 4 valence electrons. Here we have 8 valence electrons. Here we have, so these are not in the same energy level. So let's see, this would be 6 valence electrons. And here, this would be 7 valence electrons. So fluorine has 7. We want to find the element that has 7, which would be D. Okay, we actually already talked about 22 when we went through and I kind of explained on the periodic table here. So we're going to skip that one since we've already talked about it. 23 says, list physical and chemical properties of metals, nonmetals, and metalloids. So metals are lustrous or shiny. They're malleable, meaning they can be flattened into a disc. What else do we have? They're ductile, so we can draw them into a wire. They are good conductors. And they react with acid. Nonmetals are basically the opposite of everything that I just said. So they're going to be dull. They're not malleable. And the term that we use for not malleable is brittle. They are not ductile. We can't draw them into a wire. If it's brittle, if it crumbles, it would not be good trying to pull that into a wire. They are poor conductors, and they do not react with acid. Do not react with acid. Metalloids are kind of a combination of both. So properties of metals and nonmetals. All right, list of metalloids. Well, we've got, let's see, we have boron, silicon, we have germanium, we have arsenic, we have Sb, which is, can't think of that, is that? It's antimony. Why is it Sb? Who named that? Te, which is tellurium, and then Po, which is polonium. Those are your metalloids. And the metalloids, remember, are on the staircase. Okay, so on our staircase right here. All right. Where are the metals located on the periodic table in reference to the metalloids? Okay, so we got our staircase right here. They are over here. That's where the metals are. The nonmetals are located to the right of the staircase. At room temperature, most metals are solids at room temperature. Most nonmetals are gases. Identify the following based on their electron configuration. Okay, so we can just look at the last piece here. 2p5, so second row, p block, 1, 2, 3, 4, 5 is going to be fluorine. B, we can just look at the last piece, 4s1, fourth row, s block, first space is going to be potassium. And the last one, 3d8. Remember, D is always one behind, so we're going to go to the fourth period here. D block, and then 8. 1, 2, 3, 4, 5, 6, 7, 8 is going to be nickel. All right, determine the number of electrons and write the electron configuration for the ion below. Okay, so rubidium, Rb on the periodic table, Rb has, where's Rb? Rb is eluding me. 37. 37. So if it normally has 37 and it has a +1 charge, that means that it is going to have 36 electrons. Okay, RB. So let's write this out. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Rubidium is on the 5th row. So finally 5s1. No, I'm wrong. If it has one less electron, it is going to end at 4p6. So let's check this. So let's see. 2 plus 2 is 4, plus 6 is 10, 12, 18, 30, or 20, 30, 36. Okay, so we're good here. All right, phosphorus normally has 15. If it has a -3 charge, that means it has 18. 1s2, 2s2, 2p6, 3s2, 3p6. Again, we can check this by adding up all of the exponents to get to 18. Oxygen is normally 8. If it has a -2 charge, it's going to have 10. 1s2, 2s2, 2p6. There's 10. Magnesium has 12. If it has a +2 charge, it's going to have 10. Guess what? It's going to have the same electron configuration as our oxygen here. Okay, elements with the same number of valence electrons have similar properties. An element is found to be brittle, lustrous, and conducts electricity. The unknown may be, well, brittle, this is a non-metal property. Lustrous is a metal property. Conducts electricity is a metal property. So we have properties of both, metals and nonmetals. Gallium, Ga, is a metal. Can't be gallium. Selenium, Se, on the periodic table, is a nonmetal. Can't be selenium. Silicon is a metalloid that has properties of both. And then sulfur, S, is a nonmetal, so it can't be sulfur. So just to check, silicon is the correct answer here. All right, an element is to be malleable, which is a metal property, conductive, which is a metal property, and reacts with acid. That's a metal property. Well, we know it can't be silicon because that is a metalloid. Arsenic, As, is also a metalloid. It can't be that. So between phosphorus and potassium, phosphorus is on the right side. It's a nonmetal. Potassium is on the left side. It is a metal. So it has to be potassium. Okay, an element is brittle. That's nonmetal. Dull, that's a nonmetal. And does not conduct heat or electricity. That's a nonmetal. What is it? Arsenic is a metalloid. Can't be that. Calcium and aluminum are both metals. Okay, calcium and aluminum are both metals. So we've got aluminum, calcium. They're both to the left of the staircase. It can't be those. So it would have to be phosphorus. Which of the following is most likely to be a gas at room temperature? Okay, so that would apply to nonmetals. Silicon is a metalloid. We know aluminum is a metal. Magnesium is a metal. Argon, Ar, is a noble gas, which obviously the noble gas is going to be a gas at room temperature. All right, last one. Which of the following is most likely to be a solid at room temperature? Solids are metals at room temperature. Oxygen is a nonmetal. Can't be that. Chlorine is also a nonmetal, so it can't be chlorine. Gallium, Ga, is, where's gallium? Gallium's right here. Gallium is a metal, And just to check and make sure that we're not missing anything, bromine, Br, is right here, is a nonmetal. Okay, so it can't be bromine. That's it. That's the study guide.